In this tutorial, we will cover first part of making Chunhua Pedestrian Bridge in Shenzhen using Grasshopper, and we will also apply few techniques from Lunchbox and Pufferfish plugins. In case you want to see full version of this tutorial, which includes rounding corners of curved panels, cutting surface with multiple items, and making 3D each panel, you can watch extended version of this on our Patreon page, where you will get other extended tutorials with project file. Hi guys, what's up? Lazar here from How to Rhino. Welcome back to our channel. If this is your first time here and you want to learn how to use Rhino and Grasshopper, start now by subscribing and clicking the bell button so you don't miss anything, as we upload new videos each week specifically for architecture. In today's video we're going to reproduce a project called the Spring Flower using Grasshopper. It is a pedestrian bridge located in Shenzhen in China. You will also learn how to create this complex form and how to set all these divisions on the facade. If you follow all the steps, you will get results like this, and you will be able to modify the whole shape, change number of divisions, adjust thickness of the structure with the parameters that we're going to create. Let's get started. Alright guys, the first step will be to create the point. Once we have the point, we will create the circle in XY plane. By default, if you connect with the P, it will automatically create the circle on XY plane. And here we will set the radius, let's say 28 units. Once we create a circle, we'll add component C in order to modify the end point of the curve. We'll use this for later steps, but I will demonstrate in a simple example how we can do it. So if we connect end point with a circle, you can see the end point of the curve is located here. But if we connect circle with the seam and reparameterize it, so right click and check reparameterize, and in T set from 0 to 1, I will connect endpoint with the seam component. You can see the endpoint of this curve is positioned here. Basically we just adjust the endpoint of this curve. The next step is to add horizontal frames on the circle using component horizontal frames. In the N I will set 12. I will explain you why we need 12. Our idea is to create a curve like this. I will sketch like very quickly. Alright, and we will fillet this polyline in order to get shape like this. So each of these corners we're going to fillet. But let's get back why we need 12 divisions or 12 horizontal frames, because we have here 12 points. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll have 12 contour points. That's why we are going to divide this curve on 12 divisions and position these points horizontal frames. Okay, we have 12 horizontal frames and we are going to call every second one. So 1, 3, 5, 7, 9 and 11 will be in one list, and point with the index numbers 2, 4, 6, 8, 10 and 12 will be in another list. Why? Because one set of points will move along y direction of horizontal frames. So we are going to move them, let's say these guys, something like this. And after that we are going to create a polyline. In this step we can use dispatch or call pattern. Both of these method works. So I will create pattern 01, and here we have, in this list we have on these guys and the same pattern, but I will check invert to extract other set of horizontal frames. And once we have them in a two different list, we'll deconstruct plane, and as I mentioned we will use y direction. Y direction is always marked with a green color. So deconstruct y vector we will place in the amplitude, and this vector we will place in the move component. Something like this. You can see that I use here reverse because we can these y vectors pointed towards the center. So, but because we want to move them in the opposite direction, that's why I use reversed vector here, and also here as well. Okay, here we have one set of points, and here we have another set of points. The next step is to combine them into one list again. We can use a weave component with the same pattern as we use here, 0, 1. So in the P we'll place 0, 1, and in the 0 we'll connect one set of points, and in the 1 we'll connect another set of points. Once you combine them with the weave component, they will be placed again in one single list. Using these points we can create a polyline. Don't forget to set here to true in order to create closed polyline. Okay, and once we have the polyline, we can fill its corners. I will turn off all of this. We don't need this anymore. The next step is to divide this curve. I'm doing this because if we explode this curve, we'll get 24 segments if we explode it. I don't want this because I want to have only one segment. That's why we will divide this curve into, let's say, number 174. It doesn't matter, but this number should be, let's say, bigger than 100 or 150. And once we have these division points, we can use component interpolate, and also again don't forget to set here true in order to create closed curve. I will turn off this, and you can check if I connect explode with this curve, we have only one segment. All right, let me open this reference picture. So far we have this curve, so this one, we have the circle, and our idea is to create this side surface on which we'll later on apply surface division in order to create these panels. To create the side surface, we will move this curve along a z vector. So we'll have one more curve like this, and both of these curves will offset, because you can see, I will go back, you can see that here we have double line. So in order to get this part, we'll offset both of these curves. Okay, first we will move it along z vector. Okay, we'll combine them. We can use merge or entwine. It both works. I choose to use entwine component, and these two guys will offset. All right. Once we have these four curves, we are going to divide them into equal number of segments. For that purpose, we'll use component evaluate length, and in the end, which is really important, we need to set true. It means that the numbers we'll set here will be from 0 to 1. That's why we are going to use domain 0 to 1 that will be placed in the range, and in the range we'll set number 100. It doesn't matter, it just need to be bigger number than 80, for example. And these numbers we'll place in the L input of the evaluate length. So we created division points on these two curves. I will turn off this, on these two curves. So in order to find corresponding points on these two inner curves, we'll use component curve closest point. Curve will be this offset curves, and the points will be the points we get from the evaluate length component. If I turn on, you will see that we have another set of points, and once we have these two list of points, we can create a line between them. The next step is to create vertical lines like this, and these lines will connect with these short lines in order to create curves like this, because later on we are going to loft them and we will create a surface all around this circle. So we have these segments, we are missing these vertical lines, and we can create them using these points. If I connect parent viewer we can see that we have 2 branches and each branch contains 101 items. In order to create 101 branch with 2 items, because instead of having these points in one branch, we'll create these 2 points in one branch, then these 2 points in another branch. And having distribution like this, we can create the polyline and connect these 2 points. Okay, that's why I'm going to use flip matrix, and the result from here will connect with the polyline, and we have these vertical lines. One really important step which is not visible in this moment is that we have overlapping points. If I open this list of numbers, we have point at 0 value and we have point at 1 value. 0 represent the start and 1 represent the end of the curve. Because we have periodic curve, these 2 values or these 2 points will be on the same coordinate. So it means that we have here overlapping lines and here 1 overlapping lines. In order to remove line which is overlapping, we know that these lines are positioned either on the end or in the start of the list. So I will remove the last one. If you want to remove the last index from the list, you can just type -1 with the call index component. So these lines will place in the call index component and set -1. You can notice that we have 2 branches with 101 item, and here we have 2 branches with 100 items. Okay, and the same logic here. I will turn off. Okay, once we have lines like this, we can join them. I will flatten the input and join curves. All right. Using these curves, we can create the surface. But there is one step in between. I will open reference image again. You can see that these edges of the surface are rounded. That's why we're going to connect fillet. I will turn off this. And now we can use loft. So don't forget to set true in order to create closed surface. And one more thing, we will set tolerance 1 in the refit input, and in the type we will set loose. Okay. Surface generated like this, we can connect with the component from the Lunchbox, which is called skewed cuts. It's placed here. In the U we'll set 140, in the V we'll set 9. And we easily create panels on this surface. But there is one problem, that on each side we have these openings. In order to create openings like this, we need to create the curve. I will sketch here. So we need to create the curve all around the surface, and with this curve we'll split the surface and remove these parts. Okay. Now the next step is to create this curve, and these curves, it's actually a sine wave. And if you want to know more about this, you can watch one of our previous tutorial, Calatrava project, where I explain in detail how you can create sine curve in Grasshopper. So I will go back to this curve, and I will move along that vector and position it somewhere here. Next step will be to adjust the end point of this curve, because right now the end point is positioned somewhere here, but we want to adjust it and to position right in the middle here, because later on we'll create the sine curve, and it's really important to have this point in the middle here. It's very easy to adjust it using seam component. In the C we'll place this curve, but in the T we need to find this parameter. We'll take the start point of this curve and project or find the closest point on this curve. This point will be projected here using curve closest point, and in the T output get the value, and this value will be placed in the T input of the sim component. And here we have completely the same curve as we have here, but just the endpoint is modified. If I check the endpoint, you can see its position here. Alright, I will turn off this, and using this curve we will find its horizontal frames. The T will use this parameter that we'll use here for the evaluate length. So the same values we'll place in the T input, and don't forget to reparameterize this input. Alright, and we get horizontal frames. Using deconstruct plane, we'll take out the z vector, because these points we will move along z vector, something like this. And these values we need to get. We can generate them using a sine component, but first we need to create domain. Domain will be from 0.5p to 12.5p. Again, I will mention that this part is explained in detail in our Calatrava tutorial, so that's why I will go really quickly through this. If we set here 0 to 12 pi. Why to 12 pi? Because we have 20 points and it means we'll have 6 periods. For each of these segments, we'll have 1 period. I will first set 0 to 12 pi, and later on I will explain why we need to adjust it to half pi to 12.5 pi. This will be the domain, and basically values from here we will remap into this domain. So right now we have domain from 0 to 12 pi using sine component, and this is the amplitude which we are going to apply for the z vector in order to move points and create a sine wave. Okay, we have something like this. I will open again a reference picture, and you can see the highest amplitude, its position right in between these 2 points. So the higher amplitude is here. Because the sine curve starts with 0, and here is 2 pi, and here is pi. So the highest amplitude of the period is positioned here, and here we have half pi. That's why we'll start our curve. This is our starting point. We'll start the curve with half of the pi. And if we start with half of the pi, we will have curve that we want to get. I forgot to mention that these points we will use to create the curve using interpolate component. And in order to position the highest amplitude right in the middle here, we will set 0.5. Okay, and you can see all segments of this surface, the highest amplitude of the curve is positioned right in the middle. And right now we will scale this curve. I set these two scaling factors arbitrarily. One is bigger than 1 and one is less than value 1. Okay, the center of scaling will be our initial point. And once we have these two curves, we can create the surface using loft component. This surface is really important because this one, it will represent the cutting surface. Panels we get here, we will cut with this guy. So both of these outputs I will merge, and here we have panels. Using component split B-wrap, we will cut these panels from the lunchbox. I will turn on, and I will turn off these two guys. And the next step will be to remove all these surfaces in order to create these openings. You may wonder, okay, but how we can remove it? It's very simple. We will first find the center point of each surface. Then these points will project on the cutting surface. So all these center points will be projected here. And why this is important? Because we will find its projection on the surface, and based on their z vector, we will remove these parts. Let's say we have this surface, and this is its center point with z coordinate, let's say 15. If we project center point on the surface, we have this point here. Let's say z1. It has a z coordinate 12, and we will check if this coordinate is larger than this one. Keep that surface, otherwise remove it. What will happen if we have this surface? This z coordinate is, let's say 8, and if we project on the surface, z coordinate will be 14. Again, the same logic will apply. If this z coordinate is larger than this one, keep it, otherwise remove. Because 8 is not larger than 14, this surface will be removed. Alright, here we have center points. We will deconstruct in order to find z coordinate. And here we have all these points projected on the surface. We'll deconstruct points and take out z vector. And then check if this z coordinate is larger than this one, then keep that surface. So this pattern we'll use for the cull pattern. I will turn off this, and here we have only surfaces that are above cutting surface. Alright, and we created panels with openings on each side. So now I want to show you why we created this seam in the beginning, because if we change this parameter to, let's say, 0.4, the whole shape will be rotated. I mean, you can use rotation, both of these method works. In case you want to see full version of this tutorial, which includes rounding corners of curved panels, cutting surface with multiple items, and making 3D each panel, you can watch extended version of this on our Patreon page, where you will get other extended tutorials with project file. And if you made this far, thank you so much, I really appreciate you. Hit the like button if you like this video, consider subscribe if you haven't already, hit the bell button for the future videos. If you are interested in having step-by-step approach how to learn Rhino and Grasshopper for architecture, I would like to invite you to schedule your free one-on-one consulting call, where you will get all details about the course and how you can be part of it. It's the first link in the description. Last but not least, I would like to send special thanks to all our Patreon supporters. Thank you guys for supporting what we do and allowing us to create high quality content for you. If you want to get project files of this and all our YouTube tutorials, you can get by supporting us on Patreon. The link is in the description. Until next time, take care and see you soon.